Oh, good afternoon, everyone. And I want to welcome everyone to the 10th Hans Liebe Lectureship. The U.S. National Commission of URSI, with the generous support of the Liebe family, has established the Hans Liebe Lectureship in microwave and optical spectroscopy as applied to radio science, Earth remote sensing, radio astronomy, and telecommunications. This lectureship provides travel support as permissible and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the annual UNC-URSI radio science meetings. I do want to mention too that the category of endeavor for the Hans Liebe Lectureship in microwave and optical spectroscopy has been broadened slightly in this next year to include Earth remote sensing and radio astronomy explicitly. It, in previous years, was just Earth remote sensing. And so we want to point out that optical and microwave spectroscopy has, of course, many important applications in radio astronomy and Earth remote sensing. This lectureship is in honor of the memory of Hans Liebe, who was a great friend to the radio community and generously published his model in 1983, which he toiled over many years. And this model for atmospheric millimeter wave propagation is still used today, perhaps in small corrected ways, but for the most part, after around 40 years, still is a mainstay of the community. Our 10th Hans Liebe Fellow is Professor Stefan Buehler, who is director of the Meteorological Institute of the University of Hamburg in Hamburg, Germany. Professor Buehler's group began in the 1990s at the University of Bremen at the Institute of Environmental Physics. It later moved to Luleå University of Technology, Luleå University of Technology, that is, in Kiruna, Sweden. And in fact, I visited his group there in 2007. In 2013, he moved to the Meteorological Institute and Center for Earth System and Sustainability Research at the University of Hamburg. Together with Professor Patrick Arison of Chalmers University and others, he developed the ARTS radiator transfer model, which simulates the propagation of radiation through the absorbing and scattering atmosphere. ARTS is used internationally, both for remote sensing and for calculating energy fluxes, and is distributed open source as well. Throughout his career, Professor Buehler has used satellite data sets to study the role of water vapor and clouds in the climate system, and has been instrumental in developing new satellite concepts, including the Ice Cloud Imager, or ICI instrument, which will be on METOP SG. He's also parenthetically contributed to a proposal here in the US to NASA for an ice cloud imager as well. Professor Buehler currently works on the upcoming ESA Forum mission to make the first spectrally resolved measurements of the Earth's outgoing long-wave radiation in the far infrared range. He also works on fundamental topics of radiation and climate, such as radiative convective equilibrium and the Earth's spectral radiative feedback. His lecture today will be on how water shapes climate. And without further ado, it is my sincere pleasure to welcome Professor Stefan Buehler.
Thank you very much, Al, for the kind introduction. So let me try to set up so that I'm sharing my screen. So do you see my slides now in the auditorium?
Yes, everything looks perfect here.
Okay, and everyone can hear me as well?
Yes, we can.
So thanks again, Al, for the kind words on me. I feel deeply honored by receiving this distinction, and I'm particularly delighted that it's in the memory of Hans Liebe, for whom I have the greatest respect and admiration. And you will learn why during the talk also. I want to add that I deeply regret that I cannot be with you in person today. Would have been so much greater if we could have met and shared ideas, but it's simply not possible. It's frustrating for me to miss the conference, but it has to be like that. So let me launch into the talk. I want to talk about climate and water. So let me begin at the kind of beginning with John Tyndall, he who made the first measurements of the greenhouse effect. And in 1872, he wrote a book on the transformations of water. For him, it was natural to see water as something that is being shaped by the climate system as it moves around the Earth system and is transformed from one phase to the next, shaping glaciers and clouds and all these things. And this is still how most people see it today. But I would argue that it's much more interesting to turn this traditional way around, and instead of asking how climate shapes water, to ask how water shapes climate. It is water that makes our planet look like a blue marble, mostly in the vast blue oceans. And of course, that's where most of the water is, but there's also water in the atmosphere. It's a tiny amount compared to the oceans, only about 3 centimeters if it was condensed. And most of that is in the gas phase, and an even tinier amount is condensed into little droplets and ice crystals, forming the white wisps here on the blue marble. But despite this smallness of this amount, the importance for shaping our climate, it's almost impossible to overstate the importance of that. And that's what I want to talk about today. So basically, to set the scene, I want to talk a little bit about the radiation balance and about fast climate feedbacks and what they have to do with water. And then I will go slightly more in detail in 3 topics on how we can observe the spectral radiative feedback directly and what that has to do with water. Then more on the water vapor feedback, and in the end, a short part on the cloud feedback. So already Joseph Fourier, in fact, even earlier than John Tyndall, realized that the Earth's temperature, the temperature on the surface of Earth, is determined by the radiation balance. Earth is heated by the shortwave radiation that it gets from the sun, and it's cooled by the outgoing longwave radiation that it emits out to cold space. With the current albedo, the incoming net is about 240 watts per square meters. So Earth's temperature has to adjust so that the outgoing longwave radiation is also approximately 240 watts per square meter. In this simple global view, a lot of details are pushed under the rug. There's a lot of spatial detail to start with. Here's an image from Meteosat from the 6.2 micron channel, which is a reasonable proxy for OLR. The dark areas are where OLR is high. It's in the substance areas, the dry areas in the tropics. Some people have called these the radiator fins of the planet because there the emission out to space comes from low levels in the atmosphere where it's warm, so it's high values of OLR. And the white areas are the deep convective areas where little outgoing longwave radiation is emitted. If you look carefully, and if I wouldn't loop the video here so quickly to save size on the presentation file, you could also see how the circulation actually transports excess energy from the equator out towards the poles. Besides this spatial structure, there's also a lot of spectral structure. The spectrum looks almost fractal, and most of these lines are due to the dominant greenhouse gases, CO2 and water vapor. It's not really fractal because if I zoom into the spectrum, I can at some point really resolve each and every line. There's a finite number of lines here, but just very many thousands of them. So if I increase the concentration of greenhouse gases, it will decrease outgoing longwave radiation. And that means that additional energy will pile up in the Earth system, heating it up, increasing the surface temperature. And that temperature increase has radiative consequences. First of all, there's the basic Planck feedback. Warmer body emits more infrared radiation, and that helps the planet to reach a new equilibrium. But also, as it gets warmer, there will be more water vapor in the atmosphere. Water vapor feedback. Water is a powerful greenhouse gas, so that will further enhance the warming. But then, to help us a bit, there's lapse rate feedback. The surface, or the other way around, the upper troposphere will actually warm more rapidly than the surface. And that is a stabilizing feedback because a lot of the OLR comes from the upper troposphere. So if the upper troposphere warms more, the surface has to warm less. So we will get less temperature increase for CO2 forcing. And not completely obviously on first sight, but water is also behind this feedback because the global mean temperature lapse rate, the gradient here in this little graph on the top right in the box, it's set by the moist air diabet. Warmer air will contain more water vapor that condenses upon ascent and releases latent heat. And because of that latent heat release, it will not cool as rapidly as it ascends. And this profile created in the deep convective regions imprints itself on the entire tropics due to gravity wave activity. And then there's a surface albedo feedback. That is mostly the temperature dependence of seasonal snow cover. A warmer planet has less seasonal snow cover. Snow has a high albedo, so that's a positive feedback. Albedo gets lower with rising temperature. And the cloud feedback related to changes in cloud amount or cloud optical properties with temperature. So as you can see, water truly is at the heart of all of these interesting fast climate feedbacks. It completely shapes Earth's climate. In the following sections of this talk, I want to explore more this link between water and radiation and climate. So let's start with the spectral feedback. What do I mean by this? Let's start with the spectrum again. Here's a picture of the spectrum. So this is outgoing long-wave radiation frequency on the x-axis in units of inverse centimeter and watts per square meter per inverse centimeter on the y-axis. And the difference between this spectrum and the one I showed before with this zoom-in video is that this is an actual observation. The other one was a radiative transfer model simulation. This is a real observation from the URSI instrument, European hyperspectral Fourier transform infrared instrument, similar to AIRS. The black line is a real measurement. The red area of the spectrum is not covered by this instrument, so it's a statistical reconstruction based on a radiative transfer model and statistically inferring these not measured channels from the channels that are measured. The integral under this curve is the total outgoing infrared flux, which cools the Earth. And the derivative of that with temperature is basically the long wave radiative feedback of the Earth. And this is a really absolutely central quantity for our climate because it is directly related to the climate sensitivity. Climate sensitivity is the temperature increase or equilibrium temperature increase that you get for a CO2 doubling. And that is basically just the radiative forcing for a CO2 doubling divided by this feedback parameter. Now, the feedback parameter is normally thought of as a scalar quantity, but nothing prevents us from doing this also spectrally in spectral space. So just taking the derivative of this curve with respect to temperature. And that is shown here on the top left. I will explain in a minute how it's generated because this is not trivial to derive, but conceptually it's a derivative of the spectrum that is shown for reference on the right. What it shows is that the feedback is quite strong between roughly 800 and 1200 wave numbers. It's also negative, which is nice because that means it helps the planet will reach a new equilibrium. Units here are such that a CO2 forcing would be positive. So then as the Earth warms up, radiative feedback is negative, we will reach a new equilibrium. If it was positive, it would run away. So why is there so much feedback between 800 and 1200 wave numbers? It's because there is the atmospheric window. You can see that in the bottom plot, which shows the zenith opacity as a function of frequency, and where that is below 1, basically the atmosphere is transparent. And that means that basically the radiative feedback from the surface just gets through to space. Why don't we see so much feedback in the other areas that are dominated by water vapor? There's a simple and beautiful theory around this, which was developed by Simpson in the late 1920s. The idea is that temperature controls the amount of water vapor in the atmosphere. I will come back to that later. But if you accept that, temperature controls water vapor. So water vapor controls absorption. So basically temperature controls absorption. And that has the consequence that the emission out to space will happen at a fixed temperature. This is illustrated in the figure on the right. In a warmer world, everything gets warmer. And that means that the emission point where at a given frequency where the infrared radiation originates, it will just move upwards, but maintaining the same temperature. So according to this Simpsonian theory, in frequency regions that are dominated by water vapor absorption, there should be the feedback parameter should be 0. The radiation should be completely decoupled from the surface temperature. No matter how warm or cold the surface is, this emission point would always stay at the same temperature that matches this frequency. And we can actually test this model quite easily. That's the gray line here in the graph. That is the simple model that we just take the radiative feedback from the surface, which is the derivative of a Planck function for the surface temperature, and multiply that with the transmission of the atmosphere, which is quite low in the water vents, or sometimes almost 0. And yeah, then you get very small feedback. So I've forgotten to explain how our feedback curve is really derived. So the idea is that, I mean, we don't have 50 years of URSI measurements or 100 years, which we would need to determine the feedback parameter for the forced response to the CO2 increase. But we have natural variability. So here we have taken monthly mean, global mean spectra of URSI and regressed them against monthly mean, global mean surface temperature changes. And then you get this beautiful feedback curve. This technique has been used for the integral feedback parameter, not the spectrally one, by Andy Dessler in a very nice paper. Yeah, there are different sources for natural variability, seasonal variability and interannual variability, and they lead to slightly different feedback curves, as illustrated by the blue and the green line here. And the reason for that is that they have not quite the same temperature pattern. The temperature changes in the seasonal cycle and between years are different. And there is a second order effect of the temperature pattern on the feedback. This is in fact called the pattern effect, and it also plays a role for the forced response. So using this very simple theory and just using radiation transfer model, we can get quite profound insights into how this feedback works also in a more complex model. Well, I should point out one thing here. One frequency range is particularly interesting, the one, let's say, at 500 inverse centimeter and below. So this is what I've circled here. But that frequency range is actually not directly observed. It's the part that we have just statistically reconstructed. It would be really great to test these ideas of Simpsonicity and also, I mean, kind of observe, I mean, you see in these at least in these proxy observations, the feedback is not exactly zero there. And the reason is that there are subtle changes in the relative humidity distribution. And so, of course, these are also quantitatively important. So it would be really great to test that. And that is where this forum mission comes in, because we will get, when forum flies, we will get direct observations there. So this is just a fancy title slide from the user consultation meeting where forum was selected. It will be Earth Explorer 9. And it will measure exactly the missing part of the infrared spectrum. So everything that is below what URSI measures today. It has quite a lot of overlap with URSI, but it's mainly meant to be used in conjunction with URSI to then have a coverage of the full outgoing long-wave radiation spectrum. A few key facts on the instrument. It's a Fourier transform spectrometer. It will have about 0.5 centimeter spectral resolution. Will cover all the way down to 100 inverse centimeters. And will have a very high radiometric accuracy of 0.1 K. It's conceptually quite simple mission because it really will be only this spectrometer, and then there is also an embedded imager that is mostly intended to see if the scene is cloudy or not. And the planned launch is 2027. Next, I want to go a bit more into the water vapor feedback. And I've already kind of used this idea that relative humidity in the atmosphere is thought to remain roughly constant. I mean, that's the basic idea behind the water vapor feedback. Constant relative humidity means higher temperature implies higher absolute humidity, and that's creating the feedback. And it's also baked into this idea of Simpsonicity, because if the relative humidity is constant, then it is only the temperature that controls absorption. And then you get Simpsonicity. And if there are subtle changes in relative humidity, you get deviations from the Simpsonian theory. Now, if you read an undergrad textbook, it always says relative humidity stays constant because of the Clausius-Clapeyron equation, which is the equation that governs the equilibrium vapor pressure over a plane interface of liquid. And that is the equation that is in the definition of relative humidity, because relative humidity is the amount of water vapor relative to this equilibrium value. So they always say, okay, yeah, because of that, because of Clausius-Clapeyron, warmer air contains more water. But that's actually only true if you have liquid water present. I mean, it would be true close to the ocean surface. It's very intuitive that this implies. But why is the Clausius-Clapeyron equation governing upper tropospheric humidity, which is really far away from the ocean? But there's a simple conceptual model that explains this, and it's the advection condensation model. It's illustrated by this figure. As the air moves up in a convective updraft, temperature reduces, and that means the equilibrium amount of specific humidity decreases. That is illustrated by the size of the bucket here. Bucket will get smaller, and at some point it will start to overflow, and the excess water that flows out will rain down as precipitation. And then the air parcel, the bucket, will leave this convective updraft and start to slowly subside. And as it subsides, the bucket gets larger again. The holding capacity to water vapor, if you wish, although that's not physically completely correct. So the relative humidity goes down, because relative humidity is the filling level of the bucket. And this model explains basically the distribution of relative humidity in the atmosphere. Here you see this distribution. This is now based on the model simulation. You have very high, this is somewhere in the mid-troposphere. You have very high humidity in the intertropical convergence zone and in the storm tracks. And between, in the subtropics, you have very dry relative humidity where the subsidence zones are. And we can easily test this convection advection model or advection condensation model by running back trajectories. So we have a target region here illustrated by the orange box. And the two orange lines with the circles at the end are two example trajectories to show where two air parcels have come from in this target area at this moment in time. And the contours illustrate the entire source area. So it's the area where the air parcels come from, the area where they were last saturated. In the bottom plot, you can see that this source region for the orange target region is quite high. So it's deep convective regions. And so that's why this target region, the orange one in the subtropics, is so dry, because the air has left the convection and then it has subsided and has undergone this subsidence relative drying because it got warmer and warmer. So in the same paper, this is published or is under review in a paper by Teresa Lang. You can show that this model really quantitatively works very well. And it also helps you understand the differences between different circulation model simulations. And so that's great that we basically understand how the relative humidity distribution is created. And this nearly constant relative humidity distribution has really far-reaching consequences. One consequence is that the clear sky response to surface temperature changes is nearly linear. So this is, again, in a way, the radiative feedback. Radiative feedback parameter lambda, the scalar one, would be the slope of the blue line here. And this is kind of all the climate literature. Again, if you look at an undergraduate textbook, forcing response framework, they kind of take this for granted, but it's not actually obvious that it should be linear like that. Actually, you would expect, naively, I mean, thermal emission is governed by the Planck function or Stefan Boltzmann law. So you would expect this to be a sigma t to the 4 shape, as indicated by the red line here, not a linear shape. And the derivative you would expect to be sigma times 4 times t to the power of 3 and not constant. But yeah, the physics of water can explain this behavior. It's really cool because it's an interplay between the radiative feedback of the surface, which has this Stefan Boltzmann shape. It increases with t to the 4, but it has to be transmitted through the atmosphere. And the window through which this surface feedback is transmitted gets more and more narrow for a warmer atmosphere, because warmer atmosphere contains more water vapor. So this is illustrated by the large plot here. In the bottom plot, you see the transmission for different temperatures, and this yellow temperature is very hot, and the blue and purple one is very cold. And when the transmission is close to 1, you have a window. So for the cold atmosphere, window is very wide, and for the warmest atmosphere, it shrinks to basically it goes away completely. And the top curve shows the outgoing long wave radiation spectrum. It's not as easy to see there, but basically, if the response was Planckish, if the atmosphere wasn't there, the yellow curve would be much larger on the left side. It would approach this red dotted curve there. But as the planet gets warmer, more and more of the Planck curve is eaten away because the window narrows and it's not letting the radiation through to space. So this has the consequence that up to about 280 Kelvin, the spectral feedback parameter is quite constant, because it would increase because of the Planck function of the surface, but at the same time, the window is getting narrowing at the same rate to kind of these two effects, they compensate each other. But then at 280, something interesting happens, because the window is closed so much that this compensating effect, it kind of breaks down. And then you start to see more this Stefan Boltzmann behavior, that the feedback parameter increases with increasing temperature. And so this is called the state dependence of the feedback parameter. There's a lot of literature on it from the more circulation modeling community, observing this in different shapes, in different models, and with sometimes disagreeing results. One thing we found is that it makes quite a difference how you force the model. If you force it, for example, by changing the solar constant, you get really strong state dependence. But if you force it by increasing CO2, as we do with the real atmosphere, state dependence is weaker. And that we can explain as well with thinking about water, basically. If I start with the red plot here, the right plot, it shows that, basically both of these plots show atmospheric opacity, and the blue lines are the water vapor opacity, and the gray line is the CO2 opacity. And basically what's going on is a kind of tug of war or a competition for spectral space between these two species. If we increase the temperature and thus increase the humidity of the atmosphere, then the water opacity increases, and the windows where the atmosphere is transparent, they go down, they get smaller or close down. It's like kind of sea level rise in this. So the Simpsonian Ocean just gets larger, the area where outgoing radiation is decoupled from the surface temperature. And this creates the state dependence. But if we force the climate with CO2, you get what's shown on the left side. The CO2 absorption feature also changes its strength. So that means, again, with this picture with the archipelagos in the ocean, it's kind of volcanic islands. So the islands get larger. That means if the ocean level rises, but the islands rise as well, you get some compensation. So somewhat paradoxically, the ozone, although the CO2, although it's bad because it's a radiative forcing, heating up the planet, it actually also helps the planet to adjust its radiative balance, because it's creating spectral space where changing the temperature will actually change outgoing long-wave radiation. So in a way, forcing by CO2 changes is better than if we would be forcing our climate by increasing the intensity of the sun. Okay, all of these ideas, they kind of rely on that we understand the absorption of water vapor, in particular in the window and on the edges of the window. And do we really? Already quite early on, people noticed that there's something strange with the water vapor absorption in these window regions. This is often referred to as the continuum problem. Somehow there's a quite common misconception that the continuum is something additive, so that it is additional absorption in the window. But this comes from the way that modern water absorption models are constructed. It's not physically true, actually. So to explain this, consider the blue line. The blue line is a state-of-the-art full water absorption model. And compare that to the red to orange line. The orange line is what you get from a naive calculation, just assuming a Lorentzian line shape and no other corrections. So you don't get too little absorption in the windows, you get actually too much absorption in the windows with a naive line-by-line model. What the modern model mostly does is it's making a cutoff, applying a cutoff to the lines. And then there's an additional empirical term to bring it into agreement with observations. The role of that term is illustrated by the green line, because the green line shows the effect of just applying the same cutoff as this modern model is using. By the way, this is the model from Elam Law and co-workers called MTCKD. So this effect of adding the continuum term is actually smaller than the effect of just making the line cutoff. This continuum problem has a very long and complex history. Almost from the beginning, people noticed that there was absorption in the window regions. And then in the beginning is what's not so clear if what is the physical cause, if even wings of lines are strong enough to explain this. But as I said, it turned out as the line shape theory developed further, that actually simple theory predicts even too much absorption there. Then it was also, to complicate things, it was discovered that water is also forming dimers, and the dimers have also an absorption spectrum. And that explains certain aspects of the absorption in the window, particularly the fact that it has a quadratic, or some part of it has a quadratic dependence on the water vapor pressure and also a strange temperature dependence. From the 80s on, people focused on making quantitative models of this. And there, Hans Liebe really did pioneering work with his MPM model series, focused on the microwave spectral range, and still arguably the best models for that frequency range. Later on, Clough made a model for the thermal infrared using this formalism of a line shape cutoff plus continuum term. And that is basically the shape or the formulation of the continuum that is still being used today. At the time when he constructed it, there was also theory behind it, consistently applying or calculating it from a line shape correction and just fitting those line shape correction parameters. But that connection to underlying theory has now been lost, because in the years since then, people have just made empirical updates to the continuum term to bring it into agreement with observations. So we are basically just tweaking the continuum. I find this a bit dissatisfying, because it's such a central, like, cornerstone of climate research that we understand water vapor absorption. And this is simple physics. So in principle, we should be able to know this as accurately as we wanted if we were putting enough effort on it. Basically making much more laboratory measurements, but also doing more work on the theory to have a more closed formulation. I think there is a growing consensus that both the dimer formation and also the farthing behavior of the normal absorption lines, and perhaps even line mixing, play a role for this. But there's really no good comprehensive theory. It's a very empirical thing. Although the accuracy is not so bad, I would say in the windows it's on the order of perhaps 10% or so. Coming back to Hans Liebe, for myself personally, the Liebe model literally was my first exposure to this whole research field of atmospheric absorption and radiative transfer. To kind of prove this, I dug out this figure from my master thesis from 1994, where I worked on validating observations from a microwave radiometer in Antarctica, in Amundsen Scott Station. And this plot shows a comparison of the zenith opacity at 275 gigahertz, a comparison with predictions of the Liebe model based on radiosonde humidity measurements. And given the uncertainties in the microwave radiometer observations, this agreement is really, I would say it's excellent, even by today's standards. So this model has really played an important part in my work, not just then, but also over the years it has come up, again as I worked on various microwave instruments. So it's really super special to receive a Liebe fellowship now. But let me talk about one more thing before I conclude, and that's cloud feedback. For high clouds, I can make a similar argument as this Simpsonian idea. Temperature controlling water vapor, controlling radiation. Here it's in a slightly different flavor. So temperature controls water vapor, and that controls the atmospheric cooling rate. And cooling, atmospheric radiative cooling, controls subsidence. When the atmosphere cools, it also subsides, it sinks. And because of continuity, where the atmosphere sinks in the clear areas, that must be the outflow region where the convective regions detrain. So that the top of the convection is actually determined by radiation, and it's actually determined by water vapor, or by water vapor being present and creating this behavior of radiative heating profiles being tied to a certain temperature. The overall consequence of this is that the cloud top temperature doesn't change in a changing climate. This is called the fixed anvil temperature, or FAT mechanism. The concept was developed by Hartmann, and but I think the acronym is from a paper by Zelinka a bit later. And there are also refinements of this theory. Actually, it turns out it's not completely invariant of temperature. There are some adjustments. That's then called the p-hat or FAT mechanism. So that implies a quite strong positive feedback, because the high clouds will not help to I mean, if they don't warm up, their radiation doesn't change if the climate warms, so other parts have to warm more. That's one aspect we understand, but how about the amount of high clouds? I mean, the amount of high clouds could change, so even if the altitude doesn't change. One aspect, for example, if I look into models, I can look at the ice water path, so the amount of ice, which is a proxy for the presence of high clouds. And the top left plot here shows that even the present day climatology of different climate models, it really disagrees on this. And the right plot shows the feedback, so how ice water path changes for a CO2 doubling in the fourth assessment archive. And this is also all over the place. Models don't even agree on the sign. And also the observations, the bottom left, that's different sensor types, they have a quite large spread. Mostly because it's mostly infrared instruments, and they don't, I mean, the ice particles, their size is such that it doesn't interact very well with infrared radiation, or it's basically like a black body for infrared radiation. The best frequency range, it turns out, to really observe cloud ice is the submillimeter. And we will get such an instrument, the Ice Cloud Imager ICI. It's planned to be launched with METOP second generation, hopefully in early 2024, if everything works out. It's a conical scanner, indicated by the red square here. And it has channels up into the high submillimeter, really where sizes of typical ice particles are. Here's another connection to Liebe's work, because he really helped push the microwave community into the submillimeter with the MPM model series. Because already at the time when the microwave radiometers were really stuck at much lower frequencies, he already provided the propagation models for higher frequencies. So this new mission hopefully will bring us important information on clouds. But clouds are really difficult. There's not just high clouds that ICI will contribute to, there are also low clouds. And one difficulty is that clouds have a lot of structure. They have a very high amount of spatial structure, and they organize themselves. And traditional climate models have grid cells of about 100 kilometers. So not nearly resolving clouds at all. But there's hope. On this figure, one image shows actually a climate model simulation run at 1 kilometer resolution with the ICON model. It's a German climate model, or also weather model. This was released on the 7th of December 2022, so just a few weeks ago. But the meteorological conditions were from exactly the same day 50 years ago, December 1972. And that was when this very famous Apollo 17 blue marble picture was taken. And I'm always blown away by this. It's really hard to say which picture is which, and I'm actually not saying because I want to keep you guessing. But I'm just blown away that we can really reproduce this complexity of clouds now in a climate model. So it's much more pretty. Is it also better? Yes, we can show that, at least to the extent that we have tested it. This shows, again, for the example, humidity distribution. On the left, it shows the distribution of relative humidity. In the middle, it shows the spread around reanalysis. And that spread is actually quite small. That's shown on the rightmost plot. The spread is compared to the spread that you get in a traditional climate model ensemble. So this new generation of models, it's really much better in reproducing the distribution of humidity and for sure also in reproducing the properties of clouds. And it's particularly impressive that this has been achieved without any tuning. I mean, this is kind of the first time most of these models have been run. So it's very kind of a crude first attempt, and right out of the box, it's better than the established climate models that have been very heavily tuned against radiation flux measurements, for example. Okay, so let me summarize. I hope I could convince you that water is at the heart of all the interesting climate feedbacks. And by understanding water, we can really get profound insights into how these feedbacks work. And we need this. I mean, we believe our climate models not because the model is expensive and it runs on a supercomputer, but we only believe it to the extent that we understand why it's doing what it's doing. And thinking about water really helps us derive these conceptual ideas why the atmosphere and the climate model is doing what it's doing. Cloud feedbacks are really challenging, and there's some interesting satellite missions, and in combination with this new generation of circulation model, I think it provides great opportunities for research. And that's my last slide. Thanks.
Thank you so much, Professor Buehler, for an outstanding presentation on a very timely and important topic. When I look back at my own studies of spectroscopy and water vapor and my introduction to the continuum term, I always was interested in it, but I never thought it would have such important ramifications as it does today. And it's just really interesting to see that. I would like to open the lecture for questions from the audience. Anyone, please. Microphone.
Well, thank you very much for giving us this in-depth understanding. We talk about water, clouds, and all this inverse thinking that you suggested. So my question might be a little bit out of the box, but I'd be interested to hear your observation. At this point, what is the status of creating clouds and rain, synthesizing? This is a dream that mankind had for a long time. Still, we have it in places like Africa and other places. Would you suggest understanding more in depth this phenomena? We can actually go one step beyond and synthesize rain and clouds.
This is a really interesting question. I think short answer is no. I'm not very pessimistic. I'm not very optimistic that this will be possible anytime soon. But I can give a reason for that. I mean, if there is a cloud or not, it's very strongly tied to the circulation. There's a very strong kind of macroscopic control because you need supersaturation, so you need ascending air to create it. And this attempt of cloud modification, I mean, there's quite a lot of money in this. In several countries, even in Germany, they make flights to kind of either prevent hailstorms or create precipitations. It all goes out to modify the microphysical properties of the clouds. For example, if you put additional cloud nuclei in, you can get smaller particles in the clouds and things like that. So I think there's some chance to modify clouds in this way. Sometimes it works if the conditions are right. But whether you have the conditions to create a cloud in the first place, if you wanted to modify that, you really have to modify the circulation. So basically to create a strong convection somewhere. So I mean, in a way you can do it. You can launch a big fire or burn down the forest and you will get pyroconvection. So that's one way to create precipitation, but that's not what people want, probably.
Yeah, thank you very much. So we can keep the dream up for future, hopefully. Thank you much.
Thank you. Microphone. Yeah, you use the microphone, right? Yeah, thank you.
Hello, and thank you for the great talk. I was hoping to get you to comment on one proposed solution to combat climate change, which is to artificially block some of the warming through reflective aerosols in the upper atmosphere. I don't know if you're familiar with that proposed solution. I wanted to get your thoughts on it. Does it have merit? Is it completely insane? What's your thoughts?
I think it's not, I mean, physically, it's not unphysical in that sense. It works conceptually, but it may. Okay, let me give two different answers. One is it would be practically extremely challenging because you need a huge aerosol load in the stratosphere. So you need kind of continuous huge program of aircraft flying around spreading aerosol in the stratosphere, which I doubt it makes sense economically, but I'm really no expert on this at all. But another aspect is, coming back to the subject of my talk, there's a really strong link between radiation and precipitation. Basically, when you can only rain as much as the atmosphere can cool radiatively, because creating condensate releases latent heat in the atmosphere, and that latent heat has to go away. And basically that means that if you block the incoming shortwave from the sun, you are fiddling with the radiation balance, and it will not be the same radiation balance if you have, I mean, the greenhouse gas forcing is reducing the outgoing longwave radiation. If you reduce the incoming as well, you will have, again, a balance, but you will have a balance on a lower level. So the global amount of precipitation will not be the same. Not sure if I have explained this well, but basically it means you would have to decide if you want to optimize the global temperature or the global amount of precipitation, and you cannot have both at the same time. If you would really try to do this solar radiation management to keep the temperature as it is, you would reduce precipitation quite a lot globally. I can't hear you, unfortunately, without the mic.
Sorry about that. I just wanted to clarify, make sure I understood your answer correctly. Is it fair to say that there are, let's call them second order effects that are not appreciated in that kind of theoretical solution, that there's more to be seen, than just blocking that shortwave radiation?
Yeah, I mean, just saying you could not completely compensate the effect of the CO2. You could theoretically compensate the surface temperature change at the price of screwing up the hydrological cycle.
Okay.
But that's a theoretical argument. And the other one is this practical argument that it's, yeah, but I'm not an engineer, but I think it's probably not practically feasible either.
Thank you.
Thank you for the talk. A quick question. All right, so which is which? And how much computation is needed to produce such a good
okay.
version?
Can we make a survey first in the room?
Let's have a survey. I will take a survey, Professor Buehler. So those of you who think that the Apollo photograph of the blue marble is on the left, raise your hands. I'm going to roughly estimate here. I'm going to see something like about 25, give or take. Okay, those who think that the Apollo blue marble photo is on the right, raise your hands. And we have a far smaller group. So I guess you'll have to tell us.
Yes, you are really good. That's correct. I mean, the Apollo picture is the left. But then can I ask what tipped you off? That is because I find it difficult actually to say which is which.
Well, so there are 25 people I could get answers from. What did tip me off is the abruptness of the cloud boundary just over, looks like Central America. And that looks like it's an artifact. On the left, it looks fuzzier, and that looks a little more real. But it had nothing to do with the background or the resolution. It's just that that cloud feature looked abrupt and a bit of an artifact.
Mm-hmm.
Maybe others had different opinions as to why they chose the left one. But that's very interesting. May I follow up with one more question if I can, Professor Buehler?
Yes.
And that is your response regarding stratospheric aerosol injection indeed resonates, because if we cut the short wave, we're also to some extent cutting the outgoing long wave radiation, and therefore compromising the ability of reducing the solar influx. How would this situation change, you think, if the reduction in solar flux was done by scatterers at L1 between the Earth and the Sun? In other words, exoatmospheric reduction.
Yeah, but I mean, I think then my answer was perhaps not completely clear. Oh, I'm looking for this slide. So the problem is not this aerosol in the stratosphere, it will block only the short wave. So the effect on the long wave will be small. But the problem is that the incoming short wave is determining the kind of black body temperature of the Earth. I mean, what I wrote on this slide with the incoming short wave today is 240 watts per square meter. And that's an important parameter of our climate. Basically, our climate will adjust so that the outgoing long wave is the same. And basically, this number, 240 watts per square meter, is what drives our hydrological cycle. I mean, it's the engine that drives all the weather, if you wish. So if you reduce the incoming short wave, that 240 watts per square meter, it will be 235 watts per square meter, for example, or whatever you reduce it to. And that means you have less energy to drive the circulation and less energy to drive precipitation. You will have less wind on the planet and less precipitation. Mm-hmm. Okay, I don't know if that is a real problem or not. I'm really not an expert on this climate engineering or geoengineering. I just thought it's an interesting radiative aspect of this problem that you cannot. It's really it does make fundamentally a difference whether you fiddle with the shortwave side of the radiation balance or the long wave side, and adjusting one does not completely compensate for messing up the other.
Yeah, thank you very much. It's indeed a challenging question even to address. Let me ask if there are any other questions. We have one more question from one of our graduate students, Arvin.
Yeah, thanks, Prof, for the lecture. That was pretty interesting. You mentioned CO2 archipelagos, and you also had this plot and then you made this statement that it's probably better if none of them are good, but it's better if we're forcing with CO2 as opposed to forcing through the solar constant. But is this relationship between CO2 and water vapor kind of unique, or could you have that similar kind of relationship between two other greenhouse gases, such as H2O and, say, methane, for example? Could you see something similar?
Mm-hmm. That's a really good question. I mean, I think fundamentally, it's the special property of a condensable gas, also in connection with an ocean, that you get all this funny Simpsonian behavior, right? So it's the water vapor that is really special. For the other gas, yeah, it would work the same for anything. I mean, if you force with methane, if you would force enough, you would get methane archipelagos sticking out of the Simpsonian ocean here. Or, I mean, also the ozone can produce little areas where you would have a radiative feedback. That means, I mean, fundamentally, that means also that by CO2 forcing, you can never create a runaway greenhouse effect. Runaway greenhouse effect would be this idea that if your overall feedback parameter is not negative anymore, then the climate would just run away. I mean, you would get warmer world, even higher temperature, even more feedback, even warmer world, and then the oceans would evaporate. And it's really difficult to understand. I mean, conceptually, if you add more and more CO2 in the atmosphere, you are reducing the influence of the water vapor. So you are kind of, although you are forcing the climate, you are at the same time preventing the runaway. I think that's an interesting aspect of this. But we are, just to make this clear, we are very far away from a runaway state anyway. So this is more interesting for planetary research. If you think about other planets, I think this is a really universal way to think about exoplanets. They will also have this kind of competition in their atmospheres between different gases for competing for space in the spectrum.
Thank you, Professor Buehler. It is late in the day in Hamburg, and I want to, on behalf of USNC-URSI, thank you very much for your lecture. We very much appreciate you joining us today, and we look forward to future interactions with you and best wishes on ICI and Forum.
Oh, thank you very much for the wishes and also for the fellowship, of course. As I said, I feel extremely honored and extremely delighted. So thank you very much. And it was great to give the lecture.
Okay, thank you once more. This formally closes our session, so I wish you all an excellent end of the conference.
Okay, bye-bye.
Thank you. Auf Wiedersehen.
Yeah, bye, Al.